Hello community, so great that you are back. Today we make a next step. We have here the combination of RAG and reinforcement learning in a new framework. Yes, of course, we're going to combine here our ideas of MCP protocol client server implementation with new reward functions for a very particular reason. Now, you might say, why should I generate something so beautiful new, like a new framework with an interlink here of RAG and reinforcement learning methodology? Well, here one of my viewers who dared to comment here on any of my things, he had a beautiful comment. He said, look, I discovered that the agent can end an infinite loop pretty easy, MCP tools, and it's extremely hard to prevent that without hard-coded limits and loop counters. Having that prevents the agent from executing deep research or complex tasks, which defeats the purpose. What a beautiful statement, and he's absolutely right. And today we're gonna solve this problem. So, at first we have to address the question, when? How does an LLM learn for itself? When to rely on its own internal wisdom, somebody calls it parametric knowledge, versus when it's necessary to seek external knowledge like a RAG system. Plus, if you think about it, there's a third component. When should the LLM start reasoning? Because maybe it finds the solution and just by its own reasoning process, and it doesn't need to go to any external knowledge on the internet. So, rely on internal wisdom, parametric knowledge, seek external knowledge, which data sources, when, or go with a reasoning or have an interchange process of any of those three. So how does it develop here this knowledge, this intuition, this what it learns to know what it doesn't know? And on the other side, of course, we have the how question. How does an LLM decide to search? How can it do so strategically? When does it activate which of those three elements here? And can it learn to decompose a complex problem from a human query into a series of targeted questions, just like a human researcher? Does it have the experience, the lifelong experience of a human researcher? That's the wrong question. The question is, can it learn the lifelong experience of a human researcher? I want to give you here my very simple insight. Let's say we have here a human query, a deep, complex query. So what the AI does. GPT-5, for example, if you go there here with the prompt optimization, you know what happened? It decomposes here a deep complexity human query into lower complexity but multiple elements. Topic 1, 2, 3, and 4. Great. And you know what? Now the LLM has to decide what to do with the topic. If it's aware that it's not in its parametric knowledge to answer this, topic 1, it goes and queries the internet. Or maybe it decides on another topic that it will start internally to reason about this, and maybe here causal reasoning or pure logical deduction will lead to the correct solution. Topic 3, you have to query a data lake, a database. Topic 4, what GPT-5 loves to do with is comes back and asks a user, so what do you want me to do? Can you explain this? I have no idea what you want. Great. But you know, this is even more interesting. Because after the internet query and after the reasoning and after the data lake, you get data blocks. You have additional information now. And you say, hey, great, in-context learning, yeah? And I just provide everything here to the LLM. Or you go with a classical RAG system. You say, hey, no problem. I have a ranker, I have a re-ranker, I have a re-re-ranker from the first 2000 data blocks. Great. And some of you might say, hey, now, because now we have so much data. Now, finally, here we have AGI, the emergence of intelligence. And now this intelligence, it will handle this, because it's a 1 trillion free parameter trainable model. So, hey, while we scale up, somehow intelligence has to emerge. Or if you're a little bit more on the classical scientific way, you say, hey, wait a minute, let's look here at this data stream that we have now generated during the process of trying to answer here the human complexity. What kind of complexity level are those data stream and what they have inherently in their data? Let's say in the data stream we have another subtopics, 4 subtopics suddenly for the data stream 1. And again, the LLM will decide, okay, for the first one, I query the internet. For the second one, I query the data lake. For the third one, I ask the user back. And for the topic 4, I just start a reasoning process. But how does an LLM know what to do? Yes, you can design a template. And you say, hey, you make one reasoning process. No? Or you have in your template a hard limit. No? And after 5 loops, you have to end it. Independently what you have to end it. Otherwise, yeah. And so, you see, this is kind of an answer. No? If my user tells me here, hey, I've discovered that the agent can enter infinite loops pretty easy. Yes, we can see this because imagine, it's not just on data 1, you have it all in the other data blocks too. This is happening now in parallel. So, great. So what do we generate? If we go really for a deep research or explore deeper complexities, now topic 1, if the internet comes back and says, look, I have 1, 2, 3, 4, 5 subtopics now here in my data stream 1.1. Great. And it goes on and deeper and it generates more and more data. And you say, hey, wait a minute. No, this is wrong. This is completely wrong, this image, no? Because all questions are flat. You just query the internet and you get an answer. You don't get more data or more information. Life is easy. Come on. All questions are flat. One question, one simple answer. LLM doesn't need to think at all or have more resources. And since all questions are flat, all the answers are also flat in their complexity. There are no deeper complexities. Come on, let's make it simple. And because all answers are flat, let's go for the next step. So this means because all problems are flat too. It's a beautiful, simple word. Why you want to complicate AI? And since all problems are flat that we're gonna encounter with AI, you know what? That's great because we and all humans are also flat when they use AI. So we only have a very shallow level of complexity when we use AI or AGI. So therefore, it is AGI. So therefore, Sam was right. Quod error demonstrandum. We have proven it. GPT-5 is AGI. Great. Now, you might think that this was a rather flat interpretation of the world, so let's come back to science. What problems do we encounter in this image? We have a dynamic retrieval policy problem, no? Because the LLM really lacks here a learned adaptive policy to determine when to trigger a retrieval process on its own, given here the particular complexity. Normally, this decision by an LLM is heuristic-based, leading to either excessive, high-latency API calls, MCP protocols, client servers, or a simply failure to retrieve. And we also have local minimum where the LLM decides, hey, I just have suddenly one database. I only use one database out of the 1,000 database because it's a local minimum. No? And you are stuck with one database. And you have no idea what the agent is actually doing. The second is a strategic query formulation problem. Normally, everything is flat, no? Everything is single turn. Now, our LLMs, the core of the agents, no, they are not optimized for a multi-turn conversation, for an iterative reasoning on different levels of complexity, where the LLM must learn to decompose a problem. This is the first step. Formulate then a sequence of targeted queries for the specific level of complexity the LLM encounters in the human query, and then, with the result of the query, progressively rebuild context and come back to a higher level of complexity. And this is what I explained in my video, why GPT-5 fails on higher complexity, because this is exactly the step where GPT-5 fails. And in addition, we have a cross-domain generalization problem. If you really fine-tune it, it might work here on a very narrow domain, a technical domain like mathematics or the International Olympiad on mathematics. But the moment you try to generalize to different knowledge modalities, even if you just try to go from mathematics to theoretical physics, the system fails. So what we want to do is we want to move beyond human hard-coded retrieval logic with templates or whatever that you currently use for your RAG system. What we want to use the intelligence of an AI with a training process. And the only training process we know today for an AI is reinforcement learning. So we want to train here the LLMs to master here generalizable dynamic policy for knowledge acquisition. So we have here this beautiful yin and yang of RAG, whatever your RAG complexity might be, from a graph RAG to whatever, and here the reinforcement learning process for the LLM itself. Why should we build templates that are hard-coded, that make no sense for higher complexity queries? I cannot only ask queries to the AI where somebody built a template for me, for the AI to answer my queries. This doesn't make sense. I have an AI in front of me, so learn AI. And here now, you remember this is the last video. Now I continue from here, my last video. Now we pick up here our thoughts. You remember I showed you two studies. The first, we talked in detail about search R1, training LLMs to reason and leverage search engine with the reinforcement learning here, University of Illinois at Urbana-Champaign, and MCP tool bench plus here from the Ant group. And we had an idea that MCP tool call pause at case core performance for financial task. Yeah, somewhere at 25%. Great. So let's continue. So let's be clear, because I saw some of my viewers commented, so just summarize. So what happens inside the agent brain and what happens if it interacts now with the outside world? So let's say what MCP solves in the easiest case. No? Standard LLM APIs are stateless, more or less. No? And every time an agent makes a call, it has to resend its entire thought history. Slow, expansive, context window. You know all of this. Now, MCP externalizes, if you want, the LLM working memory with a key value cache. This is here that you really have, if you want a persistent session here of the agent, hundreds of small calls, you get the idea. So you have an agent with a perfect quotation mark, persistent and massive internal memory, the history. Let's call it the whiteboard. Now, the world outside of the agent, what MCP cannot solve, your outside world has an astronomical size. Ne? And now the agent policy, the learned policy of a single agent, an LLM, must now still decide what to pull from this external world and write on the whiteboard. And this is where we have now all the classical retrieval failures going live also with MCP. Because they are strategic failures. So therefore, the reason an AI agent here, a real intelligent agent with a perfect memory like one using MCP, still fails at RAG, in whatever form of RAG you have, is that the failure isn't in its memory or in the mechanical capacity of the model. The failure lies in its cognitive policy for searching. It lies here in the learning of the LLM when exactly to initiate what process. So the LLM is making poor, unguided, or maybe some naive decision, just querying here one of the MCP servers during the active process of hunting for information on the internet. Currently, our agents are at the hunter and gathering level, if you want. So what can we do about this? We need something new, and I showed you already the simpler case of search R1 in my last video. And now we're going to talk about the latest research in AI, UR2. UR2, unifying here RAG and reasoning through reinforcement learning. This is here by Tsinghua University, beautiful. And they here, Tsinghua University and Tsinghua University Institute for AI Industry Research and School of Management Science, Hebei University of Economics and Business in China. And they, August 8, 2025, give us here a beautiful new idea how we can overcome all the problems if we just combine RAG and reinforcement learning for the reasoning process of multi or single agent system. Let's start easy. And the authors of the study tell us, hey, LLMs are great, no? Whatever RAG system you have, whatever reinforcement learning method you use here, it just works great. However, please notice, those two elements are developed in isolation. But imagine if we could bring them together. Imagine we could use here the learning possibilities of an LLM to optimize its search strategy or its tool use itself without any human interaction, without any templates, without any predefined hard-coded human code. So let's enter a new framework of RAG reinforcement learning. Let's combine both of this. Let's have this yin and yang image where those systems are trained together. Now, I built now on my last video on Search R1 to tell you now what is the next step beyond Search R1 with this new publication. At first, let's talk about the training samples itself. If you read the paper, you immediately noticed UR2 doesn't treat all the training sample equally because it pre-classifies now the training data by its complexity, by its difficulty, simple, easy, medium, hard, and it employs now a curriculum learning. So you start here with the easy one, then you go to the medium one, and then you have really a lot of training data here for the hard level. You remember Search R1 trains here a unified dataset without this curriculum learning. So nice. Now, what does it bring us? The decision to retrieve is not a monolithic skill, no? It is highly dependent on the problem's difficulty, on what I call a complexity, relative to the model's parametric knowledge. Think about a little 3B model, no? Or think about a 671 billion free trainable parameter model. Now, by forcing here a specific LLM to practice here retrieval primarily on problems that it cannot solve internally with its parametric knowledge or its internal reasoning, this new method teaches now a much more efficient and, if you want, better retrieval policy. Kind of hopefully prevents the overuse and the underuse of the retrieval tool and optimizes the cost and everything together. Now, really interesting is the reward function. You remember, Search R1, we talked about a reward function, and I told you they'll use a really simple reward function here at the beginning. Now, at UR2, the reward idea is different. They have a two-step approach to this. They say stage one is what we want to reward in the very first time of the training process is simple here the retrieval activation. So we only care here about a correct tool use, about the plan how to use which tool for which particular task at what specific time in the reasoning process. It rewards your correctly formatted search queries with +3, +4 for more, and penalizes syntax error or unhelpful queries, and you get the idea. So we just go here for, if you want, correctly formatted queries. And stage two is here then finally the quality of the real answer given. So now the reward function shifts away from a correct form, from a correct plan, to the real result, to the correctness, the factual correctness of the final answer given. Easy, no? And you might say, that's interesting, because in the last video when we talked about here the result for MCP Toolbench++, the authors here decided to have here two parameters that they evaluate all the MCP tools on. The first one was here, remember, AST DAG accuracy. So the execution plan, this is exactly what we see now in this new study. And the second also was the execution result, the factual correctness of all the MCP tool calls. So what a coincidence. They both look here, both studies look here at more or less the same two parameter classes. Now remember, this is in contrast here to Search R1, where I told you they use a simple reward function. But the authors told us, hey, wait, we are planning here for the next iteration here to go for more complex reward function. So interesting. But what do we achieve with this new UR2 methodology? Now we decouple again, reduce complexities, the problem of learning how to speak the language of search, let's say MCP, from actually using the language to find the right answer. So, beautiful two-stage process. What it does, it stabilizes here this difficult initial phase of reinforcement learning training, where our agent here is just randomly exploring. So what we help the agent in its learning process by providing here dense, easy to achieve reward here in the first step for the syntax first. Then we have UR2 bootstrap here, the learning process, before introducing here a more difficult reward structure of getting here the final answer factually correct. Nice idea, I like it. And then if you want the third innovation in this new paper over Search R1 is the noisy retrieval problem that we talked about. Now this is interesting because you remember Search R1, I told you that the key technology, the key technique that they used is the retrieve token loss masking, and we went through an example. Now here UR2 has another idea. They say, you know what, we need an intelligence to do this for us. So we need a pre-process of this information. We don't want to do the loss masking at all. We have an intelligence, so we have an external LLM as, let's say, a summarizer of all the raw retrieved data. And this summarizer condenses here the retrieved text and crucially is also prompted to recognize and flag queries that are non-factual. Plus, we have also a fallback message, another signal here to the policy model. Hey, something went wrong. So, okay, so suddenly we rely on another very powerful external LLM that is doing here the job for us. Why we do this? Again, reduce the complexity. UR2 approach here simply offloads here, if you want, the cognitive burden of distilling here signal from noise from the pure policy model or pi theta to a dedicated external summarization LLM. We reduce the complexity of the job that the LLM, the agent, has to do. So this allows now the policy model LLM to focus here only on the high-level reasoning trajectory. We're always back to the same pattern of reduced complexity for AI. AI cannot handle higher complexity. Clever way to teach the agent to recognize the limits of its retrieval tool. So there you have it. You see, just another 3 beautiful ideas now building on Search R1 methodology and driving here the innovation even further. Now, I think you can still use Search R1, and it's kind of ideal when you really have a well-defined search task. If your primary challenge is here technical stability of the reinforcement loop for a clear task. It's simple, it's robust, it has a beautiful masking technique. We know it's working. And this is, I think, quite powerful for building a reliable, highly specialized agents. But this new UR2 approach here with an external LLM, please don't forget, is more of a generalistic kind. You know, an autonomous agent that learns here with reinforcement learning direct complications. It uses here the curriculum in a very intelligent way. It has a 2-step reward function to help here the learning process, initiate here a simpler learning process with the right tool use. The LLM learns to use the tools, so we do not have the problems like the viewer commented here at the beginning of my video. Now the LLM knows all of this, but you have to train the LLM on all your tool use on MCP client-server protocols. You can teach here the LLM to be intellectually frugal. Okay, I go with it. So balance its internal knowledge against the cost and the utility of external information across a wide range of problems. And you see, now we are facing here and have a solution to the problem I showed you at the beginning of the video, where I told you this when question. When does an LLM know how to have an internal parametric knowledge that it relies on? When to start an internal reasoning process with pure logic, or just go and initiate here a tool use an MCP protocol for external data. And now, of course, if you're there, you could combine both systems, no? And I can imagine a future system that combines here the best of both worlds, no? We use our UR2's curriculum to train here an agent in a perfect way. And then, if we have a real dedicated task, I would use search or one loss masking technique to stabilize here the process. Technique, sorry, a little bit of German. To stabilize here the process. So you see, so interesting to see here what are the latest steps in the development of the next generation of LLM that will be, hopefully, able to handle all those agentic tasks, all those tool use, MCP protocols, agent to agent, so much better, because currently they fail quite often. I hope you enjoyed it. It would be great to see you in my next video.